Let us know about types of relations. Let us study empty relation. Let A be the set of elements 1, 2, 3 and 4, and also assume there is a relation R in the set A. There is some connection in the elements of A, that is, some relationship R exists between 1, 2, 3 and 4. One relationship is obvious: 1 plus 1 is equal to 2, 2 plus 1 is equal to 3, 3 plus 1 is equal to 4, that is, B is equal to A plus 1. Such that R equals the set of all ordered pairs A comma B, such that A minus B equals 10, in which A comma B is a relation in set A, where A is the element 1, any number 1 or 2 or 3 or 4, and B is the element 2, which can also be taken as 1 or 2 or 3 or 4. But 1 minus 2 is not equal to 10. 2 minus 1 is not equal to 10. 4 minus 1 is not equal to 10. Similarly, 3 minus 4 is not equal to 10. That is, for no A, 1 or 2 or 3 or 4, and B, 1 or 2 or 3 or 4, A minus B equals 10 for set A. So the relation R is empty for set A. What is an empty relation? A relation R in set A is called empty relation if no element of A is related to any element of A. That is, R equals phi, where phi is the subset of the Cartesian product A into A. Let us study universal relation. A relation R in a set A is called universal relation if each element of A is related to every element of A. That is, R equals the Cartesian product A into A. Empty relation and universal relation are the types of trivial relations. What is an empty relation? A relation R in a set A is called empty relation if no element of A is related to any element of A, that is, R equals phi, where phi is the subset of the Cartesian product A into A. Let us take an example on universal relation. A relation R prime equals the set of all ordered pairs A comma B such that the modulus of A minus B is greater than equal to 0. Relation R prime in a set A is a universal relation, that is, all pairs of elements A and B in set A satisfy the modulus of A minus B is greater than equal to 0. A relation R in a set A is called reflexive if A comma A belongs to R for every A belonging to the set capital A. The relation is valid for each element also, that is, R equals the set of all ordered pairs A comma B such that 2 divides A minus B. A minus A by 2 equals 0 by 2 equals 0, which is valid. A relation R in a set A is called symmetric if A1, A2 belongs to R, implies that A2, A1 belongs to R for all A1, A2 belonging to the set capital A. Let us have an example. This relation, if valid for A, B, is valid for B, A also. That is, R equals the set of all ordered pairs L1, L2 such that L1 is perpendicular to L2. A relation R in a set A is called transitive if A1, A2 belongs to R and A2, A3 belongs to R such that A1, A3 belongs to R for all A1, A2, A3 belonging to set A. Let us have an example. The relation R equals the set of all ordered pairs L1, L2 such that L1 is parallel to L2 if valid for L1, L2 and L2, L3 must be valid for L1, L3. Let's draw L1. Let's draw L2. From relation R, L1 and L2 are parallel lines. Now, let's draw L3. From relation R, L2, L3 are parallel lines. This implies L1 is parallel to L3. What is an equivalence relation? A relation R in a set A is said to be an equivalence relation if R is reflexive, symmetric, and transitive. Let us have an example. Let T be the set of all triangles in a plane with R a relation in T given by R equals the set of all ordered pairs T1, T2 such that T1 is congruent to T2. Show that R is an equivalence relation. Let us have the solution. We know that every triangle is congruent to itself. This implies R is reflexive. Now, T1, T2 belongs to R. So, we can say that T1 is congruent to T2. Hence, T2 is also congruent to T1. This implies T2, T1 belongs to R. This implies R is a symmetric relation. Now, T1, T2 and T2, T3 belongs to R. This implies T1 is congruent to T2 and T2 is congruent to T3. So, we can say that T1 is congruent to T3. This implies T1, T3 belongs to R. This implies R is a transitive relation. Therefore, R is an equivalence relation. Let us have an example over types of relations. Let L be the set of all lines in a plane and R be the relation in L defined as R equals the set of all ordered pairs L1, L2 such that L1 is perpendicular to L2. Show that R is symmetric but neither reflexive nor transitive. Let us have the solution. R is not reflexive as a line L1 cannot be perpendicular to itself. That is, L1, L1 does not belong to R. R is symmetric as L1, L2 belongs to R. L1 is perpendicular to L2. This implies L2 is perpendicular to L1. This implies L2, L1 belongs to R. R is not transitive. Indeed, if L1 is perpendicular to L2 and L2 is perpendicular to L3, then L1 can never be perpendicular to L3. In fact, L1 is parallel to L3. That is, L1, L2 belongs to R, L2, L3 belongs to R, but L1, L3 doesn't belong to R. Let us have another example. Show that the relation R in the set 1, 2, 3 given by R equals the set of all ordered pairs 1, 1, 2, 2, 3, 3, 1, 2 and 2, 3 is reflexive but neither symmetric nor transitive. Let us have the solution. R is reflexive since 1, 1, 2, 2 and 3, 3 lie in R. Also, R is not symmetric as 1, 2 belongs to R but 2, 1 does not belong to R. Similarly, R is not transitive as 1, 2 belongs to R and 2, 3 belongs to R but 1, 3 does not belong to R. Let us have another example. Show that the relation R in the set Z of integers given by R equals the set of all ordered pairs A, B such that 2 divides A minus B is an equivalence relation. Let us have the solution. R is reflexive as 2 divides A minus A for all A belonging to Z. Further, if A, B belongs to R, then 2 divides A minus B. Therefore, 2 divides B minus A. Hence, B, A belongs to R, which shows that R is symmetric. Similarly, if A, B belongs to R and B, C belongs to R, then A minus B and B minus C are divisible by 2. Now, A minus C equals A minus B plus B minus C is even. So, A minus C is divisible by 2. This shows that R is transitive, thus R is an equivalence relation in Z.